So yesterday we made some estimates of the gravitational wave signal. That's where we ended, and we're going to talk more about gravitational waves. But I want to start this lecture just with a bit of history, because I think it's always important for students to know aspects of the history of the subject that they're working on, not just the technical details. And this bit of history, I think, is also important for students, especially students who want to become teachers, because this particular story illustrates the scientific method. It really illustrates how science works. And many people in the general public don't have a real understanding for how science operates. And here is one example that really shows how the scientific method works. It has to do with this man, Joe Weber. By the late 1950s, Weber was well known already as a extraordinary experimentalist. He made fundamental discoveries in electronics, masers and lasers. In fact, some people think he should have gotten credit for the invention of the laser, along with some of the other people who were involved. So he's a very smart experimentalist. But in 1959, he turned his attention toward general relativity. He thought that was a promising field to think about. And so he taught himself general relativity. In fact, he wrote a very nice little thin textbook on gravitational waves. It's actually one of the more beautiful descriptions of gravitational wave theory. And then he began building detectors to actually detect these gravitational waves. Beginning in the early 60s, then, his idea was to take large solid cylinders of material, aluminum he used, partly because aluminum is relatively inexpensive, and he glued to the midpoint of the aluminum cylinders piezoelectric crystals. The idea is that when a gravitational wave comes by, the aluminum cylinder is like this. Gravitational wave will, of course, try to make the aluminum cylinder squeeze and extend as it introduces those forces. And as the cylinder squeezes and extends, these crystals glued in the center, they're piezoelectric crystals, so they convert strain into electric current. And so the strain that they sense as this aluminum squeezes then can be turned into a current and then is read off in some kind of a recorder. And he worked on this for about 10 years, and then in 1969 he made the stunning announcement that he had detected gravitational waves. Now, Weber was a smart person. He said, if I build one detector, no one's going to believe that if I get some signal from that detector that it's a gravitational wave. It could be just noise from the surroundings. These cylinders were suspended on wires, and any noise could come down the wires and excite these bars. So he built two of them, one at the University of Maryland, where he was a professor, and the other at Argonne National Laboratory, just outside Chicago. They're separated by 1,000 kilometers. So if he got some sort of event or signal in one, and if he got the same kind of signal in another, separated by a large distance, he could argue that this was something coming from outside the Earth and not just a local disturbance, because what's the chance of a truck rolling by simultaneously in both places? And so he used this kind of coincident detection technique, a technique that, of course, is totally adopted in the LIGO-Virgo approach to detection of gravitational waves. And so he reported that he was receiving coincident events in these two detectors separated by 1,000 kilometers, and he was getting these events, excitations of the bar, on a regular basis. And this caused a bit of a sensation. It also appeared in the New York Times when he made this announcement. And 2 years later, he made the even more fantastic announcement that when the bars were oriented in such a way that they were perpendicular to the galactic center, remember the waves are transverse, so they only make the bars go like this. If the bar is parallel to the source, the kind of excitation induced is much weaker and is not detected by these crystals, so you only get a signal, the signal is strongest if it's coming in perpendicular to the bars. And he said when the Earth was oriented in such a way that the bars were perpendicular to the direction of our galactic center, he got more signals than when they were like this. So on a daily basis, the rate of signals seemed to go up and down and was strongest when they were pointed perpendicular to the galactic center. So he argued that the source of these waves that he was detecting was somewhere in the center of the galaxy. And this was an amazing report, because the signal that he was receiving, if there were gravitational waves, was 1,000 times stronger than what anyone could have expected on the basis of any plausible source of gravitational waves. In today's language, where we talk about LIGO detecting strains of 10 to the minus 21, he was detecting strains of about 10 to the minus 14. Huge compared to what we now today think are typical gravitational wave signals. These bars were at room temperature, and so this was fantastic. What could possibly explain these observations that he was making? So this.
Sources that were being expected.
I'm sorry.
For example, if you have 10 to the power minus 14, it was 1,000 times stronger than what was expected. That would be in the range of 10 to the power minus 17, 18, right? So.
It would mean what?
So if he was detecting something around the range of 10 to the power minus 14, and it was 1,000 times stronger than what was expected at that time. So that would make it in the range of 10 to the power minus 17, 18. Mm-hmm. So what was expected around that?
Typically supernova collapse, but now we know with better analysis that those collapses are probably even weaker than we thought in the 70s. So again, 1970, we don't know even as much theoretically as we know now. In fact, in those days, we really didn't know much at all about possible sources, but if you put in any kind of plausible numbers, like the estimates we made on that earlier view graph, there was no way you would get 10 to the minus 14 unless the thing was like, somewhere very close to us in our own galaxy. And he was seeing things on several per week, right? And the rate of supernovae in our galaxy is once every 300 years. So, the rates were just completely mind-boggling. So this discovery had two major impacts. The first was theoretical. It spurred a lot of theoretical work on black holes, neutron stars, and supernovae, simply to try to understand these possible sources. Maybe we were missing something in all these crude estimates. Maybe there was some way, some kind of sources that could produce this enormous flux of gravitational waves. And so in Kip Thorne's group, many of his students began working on perturbations of black holes, neutron star theory, and so on. And a lot of people with the best computers of the day began working on big codes to calculate supernova collapse. Of course, another possibility was that general relativity could be completely wrong. We made estimates based on the quadrupole formula of general relativity. Maybe the correct theory of gravity is something else that has a completely different approach to gravitational waves that could explain these large signals. That's what was a big issue as to what we knew about the experimental foundation of general relativity. And at that time, in the spring of 1969, I was a first-year graduate student just thinking about joining Kip's group. He invited me to sit in on the group meetings. And so I sat there, of course. I didn't have the slightest idea what anybody was talking about, right? I mean, I was just a green graduate student, and they were talking about stuff, and I'm sitting there, wow. And basically, roughly speaking, he looked around the room and pointed to me and said, "Clifford Will, I want you to find out everything there is to be known today about the experimental basis of general relativity, because maybe GR is wrong." And so that Weber basically launched my 50-year career thinking about experimental tests of Einstein's theory, because this was such a remarkable announcement, and Weber was no crackpot. He was a very serious and brilliant experimentalist. You had to take these things seriously, so maybe GR was wrong. And so I spent a large portion of my career thinking about the kinds of tests that could be done, proposing tests, working out various frameworks for understanding tests to see if that was the answer. Of course, today we know that that wasn't the answer. General relativity has passed every experiment so far. The other big impact was, of course, experimental. This announcement by Weber spurred other groups to build their own detectors. And this had a big impact on the overall field of gravitational physics, because in those days there were very few people working on experiments. Only a handful: Weber, Robert Dicke, Brzezinski in Moscow. Just a few people were thinking about experiments in gravity. In the 1970s, this field was dominated by theorists. Okay, very few experimentalists. But because of this amazing announcement, many people started building gravitational wave detectors, and these were scientists from other fields of physics, like Edoardo Amaldi in Italy from particle physics, Bill Fairbank at Stanford, who was a low-temperature physicist, Tony Tyson at Bell Laboratories, who was an astronomer, and Dick Garwin, an expert on NMR and nuclear physics. They all started building their own gravitational wave detectors to try to check Weber's results. So this brought a whole new band of experimentalists into the field, and that was the beginning of the development of experimental gravity as a major part of our field. So it was another big impact of this announcement. And the thing is, by the 1980s, all these new detectors that were built, many of them much more sensitive than Weber's, some operating at low temperatures to reduce the effects of thermal noise. Weber always worked at room temperature. Some of these were done at liquid helium temperatures. Nobody found gravitational waves. And the upper limits on the flux of gravitational waves kept getting tighter and tighter and tighter, way below the levels that Weber was claiming. And so by the 1980s, a consensus developed that he had not detected gravitational waves. No one could ever find any kind of smoking gun to say, oh, here was the error that you made in claiming these signals. What most people believe was that he was using shoddy statistics for example, when you want to claim a very weak signal in the background of a lot of noise, you should set your thresholds for what you want to claim before you do the experiments. But he was determining thresholds after he saw the strip chart recorders. Those are the days of strip chart recorders, where the data was put on a long strip of paper with a pen going up and down. You know, these were the 70s. You didn't have fancy data collection techniques. And so he was setting thresholds after he looked at the data, which is really not something you should do statistically. And there are many other statistical issues. He was claiming correlations in his signals with the direction toward the center of the galaxy. He claimed there was a strong correlation in the number of signals with the direction to the center of the galaxy. But these correlations were rather weak, and they were kind of done in a funny way. Tony Tyson pointed out that he did an analysis of Weber data. Weber did share his data with other people. He did an analysis and found that there was an equally strong correlation in Weber's data with the price of pork futures on the Chicago Commodities Exchange. So again, you have to be careful when you talk about correlations. You have to understand the statistics very carefully. Meanwhile, of course, but work on these kinds of detectors continued for about 25 years with better Weber bars, better instrumentation, low temperatures, more sophisticated techniques, each one continuing to reduce the upper limits on a gravitational wave flux, but no detections. But around the same time, people started thinking about an alternative way to detect gravitational waves using laser interferometry. There was early work done in Russia by Gertstein and collaborators. Robert Forward at Hughes Aircraft, who was a former student of Weber's, started to think about laser interferometers. And Ray Weiss at MIT also began thinking about laser interferometry as a way to detect gravitational waves. And during the 1980s, Ray Weiss, who then convinced Kip Thorne that this was a promising technique. Ron Drever in Glasgow was also working on these things. They began to think of the idea of building large-scale laser interferometric observatories. There was a long period of time, of course, convincing the US government through the NSF to fund such a major project. They were talking about $350 million for the initial construction and operation. This was, at that time, the biggest physics project that the NSF had ever undertaken. And so you can understand there was a certain amount of convincing that had to be done to have them take such a great risk. But finally, the proposal was approved, and between 1994 and 99, LIGO was constructed, the two observatories. Then there was the first science run, began in 2002 and ran until about 2010. Meanwhile, during this early 2000s, most of the Weber bar detectors were phased out. It was clear that the real future lay in laser interferometry, and many of these groups phased out the Weber bars and then joined into the interferometry effort. So today, I think there are no Weber bars in operation anywhere in the world, except in Brazil and in Holland. They're working on a different design, spherical solid bars. But I think all the others have now been shut down. The last one, the Auriga detector in Italy, was shut down a few years ago. And then between 2010 and 2015, LIGO was shut down, and also the parallel detector in Italy and Virgo were shut down to reconfigure them in their advanced format, improving the sensitivity by a factor of 10, better lasers, better seismic isolation, better mirrors, and so on, heavier mirrors. The idea was then to upgrade to a level where you have a better chance of detecting gravitational waves. And then as you all know, unless you've been living on Mars for the past year, in 2015, September 14, 2015, they detected the first gravitational wave signal from a binary black hole in spiral. But when people, especially when I give talks to the general public and you just talk to people who don't know much about science, there's always this lingering feeling that, you know, when some big shot scientist makes a statement you have to believe it because it's an authoritative person who makes some statement. And we all know that's not how science works. In fact, the bigger the big shot when he makes a statement, the more other scientists try to prove him wrong because you like to bring down a big shot. But it's really the statement that you make an extraordinary claim, you have to have extraordinary evidence to support it, and you also need to have independent evidence. And so you should even keep in mind that this detection by LIGO in 2015, I mean, it's pretty overwhelming. It's pretty clear that it really is right, but you should reserve even a corner of skepticism in your minds, because one needs to confirm these detections independently. And even though the second detection in December of 2015, you might say, oh, that's confirmation because it was another detection, but it's a detection by the same instrument. So keep a little corner of skepticism open. Let's wait until maybe Virgo is back online about a year from now and makes a detection simultaneous with LIGO, and maybe when future detectors are on board. So, you know, you need to confirm by independent experiments some big claim like the detection of gravitational waves. I mean, the corner I'm leaving open is pretty small because it's so convincing, and I'll show you, later, and you'll hear more about this next week, but still, you know, science operates by confirming results with independent observations. Okay, these interferometers that were developed, again, you hear much more about these next week, but I'll just very briefly review the LIGO, the two LIGO instruments. These are laser interferometers, 4 kilometers long, in Livingston, Louisiana, and Hanford in the state of Washington. There's Virgo in Cascina, which is a village just outside Pisa in Italy. That's a French-Italian collaboration with arms 3 kilometers long. There's Geo 600 in Hanover, Germany. It's a 600-meter instrument built by a British-German collaboration. Today it's used mainly as a test bed for advanced techniques that could be used in next-generation interferometers. Yeah. So you have this cylinder of some solid material. When a gravitational wave comes into the board, it wants the cylinder to squeeze and stretch, okay? Now, if you squeeze it, it means the atoms are getting closer together or being pulled farther apart. Now, piezoelectric crystal is something that you glue to the surface, and this is one of these crystals that if you try to squeeze it, it generates an electric current. And if you stretch it, it's a special kind of crystal. And so you just attach it to an electrode and to a recorder and measure the currents. Later generations of these bars, instead of this, found that there were you had better properties, less noise and things, if you attach some sort of a motion sensor to the ends of the bar. This could be something that's like a very little mass attached to a little fiber, so that when this moves by a tiny amount, if you do this at resonance, this starts moving by a big amount. right? No, because these are resonant bars. In other words, they respond only at a resonant frequency with some bandwidth. So they really just see the strength of the signal at that frequency. Unlike the interferometers, which actually measure the waveform because the mirrors just move freely as the wave passes by. So here, a wave that arrives at this detector at twice the normal frequency hardly excites it at all, because it's a resonator, so it only responds at its frequency. Sorry?
The noise source has to be of the same frequency as the resonant.
Well, I mean, of course, a bar like this has noise at all frequencies. There's white noise just from the thermal excitations, but there's certainly then a component at that frequency that you have to worry about. Yeah.
Why didn't you just build an advanced version of this technique instead of switching to lasers?
I mean, I think there are a couple of reasons. One, I mean, as I said, during the next 15 years, many advanced versions were built, and people felt that, you know, by the 2008, they had really reached the level, and no one had any good ideas for how to go further. And secondly, because these are resonant, you only see the wave, you know, within a small bandwidth of frequency. And it was really realized, especially because people were starting to think about in-spiraling neutron stars as a source, that you really want a broadband detector to detect the signal at a range of frequencies. And this is clearly better. I mean, supernovae are fine. You know, if supernova, it emits at a wide spectrum of frequencies, but if you can see it at one frequency, that's great. But you'd like to look for more stuff than just supernovae. And with these in-spirals as a potential source, this is clearly a better technique. So a variety of reasons cause people to think that you should go this way. Of course, there's a counter-argument. This experiment probably cost $100,000 to build and run, and this cost $350 million. Initially, it's up to about $1 billion. I mean, it's big science versus small science. But sometimes to answer the scientific question, you have to, you know, build something big. So there's a variety of reasons. So there's GEO 600, and then there are two detectors for the future. There's Kagra in Japan, that is, it's an underground detector built in the same in the Kamioka mines, where so many of the dark matter and neutrino and proton decay detectors have been built. The idea is to go underground, which helps to reduce certain kinds of seismic disturbances. And the long-term goal there is also to have low-temperature techniques to cool the mirrors to reduce the effects of thermal noise. Construction is complete, all the beam tubes are in, and I think they're now beginning to install the interferometry, all the lasers and equipment. I think the initial plan is to run at room temperature for a while and then install the low-temperature stuff, but it will be online pretty soon. The arms are 3 kilometers long. And of course, there's LIGO India. And this was an idea that was floated originally, I think, by Jay Marks, who was the director of LIGO at the time. They were building all the advanced LIGO instrumentation, including the 2 interferometers at Hanford. Hanford had a 4-kilometer interferometer, but also a 2-kilometer interferometer. Separate lasers, separate optics, separate mirrors, but all within the same beam tube. This was built at that time for redundancy, basically. But they realized that if they were really going for the higher sensitivity, it's not clear how much you gain with this 2-kilometer arm. And so Marx proposed, why don't we build the stuff, put it in cold storage, and offer it to some other country, especially one in the southern hemisphere, because then by triangulating the arrivals of signals, you get better angular resolution on the sky. If we can convince somebody in the southern hemisphere to build a LIGO, we will just give them as a gift all the instrumentation to put into the beam tubes. They first talked to the Australian government about it, because there's been for many years an active interferometry group there. They have like a 40-meter or 60-meter prototype in Perth, Australia. And they very actively tried to get the Australian government to do it. And at the end of the day, Australia turned the NSF down. They're really committed to radio astronomy as the area where they invest in big science. I mean, Australia is one of the leaders in radio astronomy, and they've decided not to go with big money into gravitational waves, although they do still support the small effort in Perth. And so they turned to India, and led by our very active Indian colleagues, including Bala Iyer, the Indian scientists really went to the government and started to push for India to accept this and build a LIGO India. And the proposal marched up the chain of command through the various levels of the Indian government. And in the last year or so, I think it had been stalled a little bit in getting all the final approvals. But of course, 1 week after the announcement of the detection by LIGO, Prime Minister Modi signed the MOU with the NSF. I think the Indian government saw the train leaving the station and decided it was time to really hop on board. But that will be extremely exciting when that is built. I think the goal is to be online around 2020, because then with this array of 4 detectors, and especially with one that breaks the plane between Europe and of the Northern Hemisphere, having that one out of that plane really improves the angular resolution, and that helps you to do astronomy, to locate the source in the sky, and then ask other kinds of astronomers to look in that region of the sky. If you've seen the sky location for the detections of LIGO, these are not circles in the sky, they're these long bands, too big for any astronomer to actually try to detect anything in that region. You really want to narrow it down. A Southern Hemisphere detector really breaks those degeneracies. Okay, well, those are words. What does an interferometer actually detect? So the idea is to send a beam down one arm, have the beam come back. So when that beam comes back, its phase is changed by 2 pi times the frequency of the light times twice the round-trip travel time. And if you have that beam split so that it has the same phase going down another arm, then when that beam comes back, it's accumulated an amount of phase given by twice that travel time. And so the difference in phase when the 2 beams recombine at the beam splitter is simply given by this. 2 pi times the light frequency times the difference in travel times. Well, we know how to compute these travel times because we know the length, the displacement of each mirror at the end of the system. C1 is displaced by the unperturbed C, which is the unperturbed length times the unit vector along that arm, plus the contribution of the gravitational wave, the TT part of HJK, dotted into that unit vector. Similarly, along the other arm, it's the same thing, the unperturbed piece plus the bit contributed by the gravitational wave. Now, we don't really care about the displacement in a direction perpendicular to the mirror. That doesn't have any effect. We only care about the displacement along the arm itself, because that's going to change the length. So you take the dot product of this with E1 itself, that's the delta L, and similarly here. So when you work that out and take the difference, you discover that the phase change is equal to this factor. It just depends on the laser frequency, the unperturbed length. This difference, there's an E1K and an E1J from taking the dot product. This minus that times our signal in the TT gauge. And if I factor out the G's and C's and the distance to the source, then this really just depends on the amplitude of the gravitational wave, and so we get this formula. So this is kind of the driving signal that an interferometer will detect based on the vectors that tell you the orientation of the 2 arms and the gravitational wave signal and the distance to the source. But we'd like to connect this signal to the properties of the source itself. And so we'd like to use some kind of a basis where this is a meaningful quantity in terms of the source's behavior. Is it a binary system? What are the orientations? What's the source basis in which this thing is calculated? So to do that, we transform ourselves, or we consider the transformation between the interferometer basis. There's the interferometer, and there's the vertical, perpendicular to the surface of the Earth. We assume our source is in some direction in the sky, given by an angle phi and an angle theta relative to the detectors. So we can define a basis on the plane of the sky that by simply doing the rotation. First we rotate about E3, and then we rotate down by theta. So that gives us a new basis on the sky, where the new E3 is the direction to the source, and E1 and E2 prime are in the plane of the sky, but oriented just by these rotation matrices that you need to first rotate this way. So E1 goes here, and then when you rotate downwards, E1 points down, and E2 points that way, prime. But in the basis on the sky, of course, our source may have its own basis that's connected to the nature of the source, depending on the source details. So on the sky, to kind of link to the source, we want to rotate these things to a new basis, E big X and E big Y, that somehow link to the source. And so there'll be some phase angle psi that does that. And so you can, and when you do that, you can show that this TT part of AJK in our detector basis is related to the A plus and A cross that you would get in that source basis. So that'd be a basis where, the Z direction is the same, and, the little matrix is just A plus A cross with zeros here. That would be in the source basis. You can show that they're connected just by these basis vectors. It's the jth component of E capital X, and so on. And you can work out all these angles in a very straightforward way. It's in Poisson and Will. So at the end of the day, you plug this into here, and you get a formula that involves just angles. It's the dot product of this, the contraction on JK of these vectors with all of these vectors. And so you get a whole bunch of functions of angle times your two modes, A plus and A cross. And these Fs are called pattern functions. So they depend on the orientation of the detector, or the orientation of the source relative to the detector, and also the orientation of the source basis relative to the sky basis. And so depending on the orientation of the source, for a given A plus and A cross, the amount of signal you get will vary as a function of theta and phi. So the detector has different sensitivities depending on where the source is in the sky, but these are factors that you can calculate in this way. So that gives you a relationship between the fundamental source amplitude and what you're detecting through your gravitational wave detector. And this again is an example of what I say when I talk about observable quantities. This phi is an observable quantity, right? If delta phi is 0 or pi, then you get a bright spot. The two waves are in phase. If 0 or 2 pi. But if it's pi, or say 3 pi by 2, then the two light beams interfere destructively and you get a dark spot. And light and dark is a physically measurable thing. And so this is a gauge invariant, physically measured quantity. And so we've related to our wave amplitudes. Okay. Well, talking about detection of gravitational waves, I should also not neglect two other important ways of detecting gravitational waves today. Today, one of them is in the future. This is ELISA, a space interferometer. The idea is to put 3 satellites into orbit. They will orbit the sun in such a way that the 3 satellites always maintain a fixed orientation. They always reside on an equilateral triangle. The vertices of an equilateral triangle, and as they orbit the sun, they kind of rotate around slowly, and the plane of this orbit kind of also rotates slowly. The plane of the orbit is 60 degrees relative to the ecliptic, and this is actually a problem in Poisson and Will to actually solve for this using standard Newtonian theory. It's an extremely cool problem in orbits in Newtonian theory, finding these LISA orbits. I'm not sure who found it originally, but it's a very nice problem to work out. So I urge you to do it. If you haven't done it in the tutorials, you have the problem in the handout, so you should go home and work it out. It's really nice. And so they stay on this perfect equilateral triangle, roughly essentially the same distance from each other, to first order in perturbation theory. And the idea is then you have a laser here that sends toward each satellite laser beams with precise phase determinations, the same phase on each beam determined by the splitter here. At the other satellite, of course, you don't have a mirror to bounce the laser beam. Over 1 million kilometers, the signal received is so weak that if you tried to reflect that back, the signal would be beyond weak and undetectable. What you do instead is you have the signal received by a little mirror that bounces the very weak signal around some internal optics and then interacts with another laser in that spacecraft that is phase locked to that beam and then sends back another beam with a precise phase, but of course with the total power so that the return beam can be detected here. So whereas a mirror maintains the phase just by reflection, here you use lasers to produce another powerful signal back, but it's phase locked to the incoming signal. And there's a lot of optics that go into making that work. And then the same down here. These, the angles here are 60 degrees. And this project has been adopted as a project for what the European Space Agency calls its L3 mission, the third large space mission that it plans to launch. L1 was a mission to Jupiter for a few years from now. L2 will be an X-ray type satellite launched around 2028. And the plan for the L3, a gravitational wave mission, would be a launch around 2034. Now, that's quite a long way off into the future, especially for someone of my age. But for people of your age, you might well be around to see this launch. And there's some hopes that maybe the launch date can be advanced somewhat. The other hope, of course, is that this really works well if you can make this a symmetrical arrangement so that each satellite has the same capability and is sending laser beams all the way around. So you actually have 6 beams in this system, 2 in this direction, 2 in that direction, 2 in that direction, that improves the angular sensitivity, overall sensitivity, improves the angular resolution, improves redundancy, and so on. And so one of the hopes is that NASA, which has committed itself to be a junior partner in this project, that at the end of the day, NASA might contribute enough money to restore this arm. The current baseline project is just a 2-arm interferometer, but maybe by the end, it'll be what the original LISA was supposed to be, a 3-arm system. The goal of LISA is to detect gravitational waves in the low frequency band between about 10 to the minus 4 and 10 to the minus 1 hertz. So it's like radio astronomy versus optical astronomy. LIGO detects in the 30 to 1,000 hertz band. This is 10 to the minus 4 to 10 to the minus 1 hertz, looking for waves from supermassive black holes and other things. At the very, very low frequency end, the nanohertz end, is pulsar timing arrays. And here the idea is to look at is to observe with radio telescopes an array of pulsars around the sky, the most stable ones you can find. So they're like perfect atomic clocks all the way around us. They're in our own galaxy. But then as a gravitational wave comes by, roughly speaking, when it passes the Earth, it makes the clocks on Earth fluctuate a little bit compared to those pulsars, and you see fluctuations then in the periods of the pulsars that you're detecting. And it turns out that by simultaneously looking at pulsars distributed around the sky, you can look for real signals in the gravitational waves at these low frequencies, produced by things like the early binary motion of supermassive black holes, and maybe even look for a cosmological signature of gravitational waves from the early universe. And this is a very active project moving forward. The telescopes, most of them all exist, of course, but really it's building up the infrastructure, improving some of the sensitivity and instrumentation at some of these places, discovering new pulsars with very stable pulse periods, and so on. But it may well be that in the next few years, they will be in a position to report detections, but at the nanohertz level, very, very low frequency. And of course, as I'm sure you all know, LIGO detected gravitational waves, and I'm sure you'll hear more about this, but I'll just give you my take. So, summer of 2015, LIGO began its operations in the advanced mode with all the advanced instrumentation in there. The early phase, of course, was just engineering runs where you make adjustments to all the various pieces of the equipment and make sure it's running properly and optimize all the parameters that go into it. But on the 14th of September, very near the end of an engineering run, they had not yet begun the official science phase, but the science phase was supposed to start within a week or so. But at this ending part of the engineering run, they weren't turning any knobs. They were just letting the detectors sit there. So they were very quiet, operating at the best sensitivity of that moment, and nobody was touching them or interacting with the detectors. So they were effectively in science mode, even though the official date hadn't started, and a signal was seen in both detectors. It arrived first at the Louisiana detector, and then 7 milliseconds later was seen at the Hanford detector, which tells you that the signal was coming from the southern hemisphere. And the signal was the same in both detectors, essentially. And what you see here, this is not the raw data, but it's the data after doing a bandpass filter just to eliminate frequency components at low frequencies below 10 hertz and at high frequencies above about 350 hertz. So it's kind of just a smoothing of the data to get rid of really, really high frequency noise. But other than that, that's it. And so what you see is the noise of the detector, but then you clearly see a signal that rises in amplitude, increases in frequency, and then there's a little decaying bit of radiation at the end. And you can see the scale here is like tenths of a second, so you can't see the time shift, but it's really there. If you shift the two waves, then they exactly overlap, except for one thing. If you shift them by 7 milliseconds, then the Livingston signal is the negative of the Hanford signal. So they're not exactly the same. One is minus the other. But that's exactly what it should be. Because on the surface of the Earth, the arms are oriented like that, as it turns out. If you just look at the map, this is how the arms are oriented. If they were oriented like this, so that the vertex is opening and they're parallel to each other, that was a decision taken early on to make the arms parallel. That increases the chance of detecting a gravitational wave, but you lose the chance to detect both the plus and the cross mode. Two strategies they picked, the idea of getting the same signal was more important. If they were oriented like that, you would get exactly the same signal in both detectors, because it would squeeze and stretch the arms the same. But the actual detectors are oriented like that. So, and the convention is you take this minus that. So here you're taking that minus that, right? Well, if you remember that ellipse, the ellipse is squeezing this guy and stretching that guy. Well, here it's squeezing this guy in the same way, but this is the number one arm. So when you do subtraction, here you get the negative of that. So you take an ellipse like this, rotate it by 90 degrees, plus goes to minus. That's all it is. And the signals are exactly the minus sign. So in this chart, they've done the 7 millisecond shift, flipped the LIGO, the Livingston signal by -1, and you can see how they just track each other beautifully. So it's really the same signal in both detectors. And what you see here, the curves here, the little yellow curve here and the blue curve, is the best fit to this signal based on solutions from general relativity using a combination of post-Newtonian theory for the earlier part and numerical relativity for the later part, put together in a series, a library of template waveforms, theoretical waveforms, and you just compare one after the other until you get the best fit to these two signals. And so you can see how closely the theoretical one tracks the observed one. But then with that fit, your best fit theoretical signal, you can read off from the calculations what the properties of the source were. And so the result of that was that the two masses were 36 and 29 solar masses. Here are the error bars. The final mass of the black hole, which you can learn by looking at the final bit of gravitational waves emitted, was 62 solar masses. The spin of the final black hole was 0.67. This is in units in which the maximum possible spin is 1. 0 would be Schwarzschild. The distance, just based on the amplitude and knowing the masses, was 1.3 billion light years, 430 megaparsecs. And the luminosity of the signal, ergs per second, at the maximum was about 3 times 10 to the 56 ergs per second. Now, when you think about the fact that when people in astrophysics talk about extremely powerful sources like gamma ray bursts, they're talking about 10 to the 51, 10 to the 52, and then maybe 10 to the 53 in very extreme cases. So this is, as many as 5 orders of magnitude stronger than some of these things that people always talk about as the biggest explosions in the universe. So this is amazingly powerful. And the obvious conclusion that this is a binary black hole merger. The merger because you see the frequency going up and up because the things are going faster and faster. The signals are getting stronger because they're going faster and faster, emitting stronger gravitational waves. And you even see the bit of the ring down. The final black hole is produced in not a pure Kerr black hole state. It has to oscillate a little bit to shed all those excess multiple moments to settle down. And that produces a characteristic signal called a ring down signal that was also seen. So it really was a beautiful result. And you'll see this again tonight if you're coming to my lecture, but I'll just play it again anyway. So what you'll see here are simulations, including the sounds that would be produced at each detector. You'll see a trace that shows that signal. You'll also see a power frequency, a time power plot that illustrates the power in the signal as a function of time. And you'll hear it also. What you'll hear first are the real signal at the real frequency that was emitted. It's around 100 hertz, but that's very, very low. It's a sort of a very deep, at the very lowest point of our audible register. So if you listen really carefully, you might be able to hear it. But then they've taken the same signal and just multiplied the frequency by about a factor of some, so it's in the center of your audible range, so you can really hear it as normal. And it'll play a few times, so you should be able to hear it. I should turn on my... Okay, so let's of course, what you mostly hear is the noise, right? But then you hear the, that's the real signal translated into a sound, and then the next one was at the higher frequency, so you could hear it better. But this is listening to the universe. I mean, it really is cool. Okay, just a few details, and I'm sure Sathya will tell you more about this next week. The signal-to-noise ratio was 24, extremely high. This is a very strong signal, much stronger than they would have ever expected. The statistical significance was a sigma of 5.1. Doing the statistics, you can ask, how often would you get exactly this signal just by some random, accumulation of random noise? And that's called the false alarm rate. It would be 1 every 203,000 years. So, I mean, it means the chance that this was just some fluke is very low. It's not zero, of course, and it's never zero, but it's very low. Notice that you might worry that something doesn't add up. The initial black holes were 65 solar masses. The final black hole was 62. What happened? Well, 3 solar masses were converted into pure energy in 0.2 of a second. That's that 10 to the 56 ergs per second luminosity. That is more power during those 0.2 of a second. It was putting out more power than all the stars in the observable universe. Think about it. Add up the output of all the stars in the observable universe, and this is more for 0.2 of a second. sadly, all that power went into gravitational waves, which are unbelievably weak, right? And by the time we got to us, it took a LIGO to detect it. So, you know, you can put a lot of energy into gravitational waves, but it's hard to get any energy out because the waves themselves are so weak. They carry a lot of energy, but they're very weak. It's the first detection of a binary black hole. We have lots of confidence that black holes exist, but there was no knowledge that binary black holes existed. There was no evidence up to this point that such systems exist. So it's the first detection of that. And the masses are actually larger than expected. We think stellar mass black holes should have masses between 8 and 15 solar masses. It's actually a bit of a challenge to understand how you get black holes of this mass. It has to do with if you have a collapse to produce a black hole, you need gas that is very low in metals. Metals meaning anything above helium. Because metals tend to reflect light, so as the collapse goes on, the system heats up, the radiation generated by that heat scatters off the higher Z elements and produces a pressure that then blows a lot of the mass off, so that the mass that continues to collapse is rather small. So you get 8 to 10 solar masses. But if you have a system that's pure hydrogen and pure helium with very little of the heavier elements, then that particular effect is much smaller, and so maybe you can get these massive black holes by collapse. It's hard to make black holes grow from 15 to 36 solar masses. Accretion is not an efficient process for growing black holes. That's always been a challenge, especially for supermassive black holes, how to get them to grow. So this has already gotten a lot of astrophysicists involved in trying to understand such a high mass system. The second system discovered in December was much more like normal masses, 14, and I forget what the other one was. And of course, this affects the detection of this single event allowed you to revise the event rate of such events to somewhere between 2 and 400 per cubic gigaparsec per year. Okay. And this data is actually publicly available. I think they announced that after this detection, this will be available, so you can go in and analyze it using your own methods if you wish. Okay. So this, of course, has to do with the signal that's received on Earth, right? But now we want to talk about not the waves themselves, but the various quantities that they carry, such as energy, angular momentum, and momentum, and then toward the very end, think about what that means for the source that did the emission. And so using the framework, the post-Minkowski and post-Newtonian framework we've developed, we can calculate, for example, the energy flux. And you remember dE dt is, since E is the integral of tau 0, 0 d3x, this is the thing that contains matter, Landau-Lifshitz, etc. D by dt of this is just the partial of that. Because of the gauge condition or the equation of motion, this partial could be turned into a divergence of tau 0j. That can be converted into a surface integral. And so dE dt is related to this surface integral of the energy flux integrated over a two-sphere. Similarly, the momentum can be written as the rate of change of momentum of the source is an integral over a two-sphere of the momentum flux. The jth component of momentum, and k is the direction of the flux, then you integrate over a two-sphere. And finally, the rate of change of angular momentum can be calculated in the obvious way. It's anti-symmetric on j and k, as this is the angular momentum tensor from which you can construct the vector. And so, again, it depends on the flux, these guys at infinity. So all you have to do is plug in this case, all you need, it turns out all you need is the Landau-Lifshitz part. So you look up once again the formula for the Landau-Lifshitz pseudotensor and start to plug in. We know what our field looks like, our H, so you just plug it in there. But things, of course, simplify. This looks horrible, but it simplifies as long as you use a lot of the rules that we've been developing. First, we remember that this Gothic G is just eta minus h. So any derivative of g is simply a derivative of h. We also know that all we care about here, if we're calculating the energy flux, for example, is the contribution to this stuff at order 1 over r squared, right? Because this surface element is proportional to r squared. So anything in here that goes as 1 over r cubed and higher, we can throw away, because that'll be 1 over r, and we're assuming this surface is at infinity, where our detector lives. So we only care about stuff that's 1 over r squared. And we also know that g already varies at 1 over r, right? It's h, and we know h goes as 1 over r. So when we take derivatives of this thing, all we care about is keeping the 1 over r part. Any 1 over r squared part we can throw away. So each of these products of derivatives is already 1 over r squared, so we can ignore any higher order stuff in r. And furthermore, since this combination is already 1 over r squared, here we've got some regular metrics, and we can just replace all that with a Minkowski metric. Okay, so just keeping the 1 over r squared part allows you to simplify this thing tremendously. And then use our rules. If we have a time derivative of something, well, that's a time derivative, we keep it. If we have a spatial derivative, we use our rule that a spatial derivative is just minus a unit vector times a time derivative, because we're throwing away anything higher in r, 1 over r. And the final step is to use the fact that because of the gauge condition, a time derivative of something with a 0 index is equal to eta times the time derivative of the thing with the j index. So that's the gauge condition. So using all these rules, you can simplify this expression down into a much simpler object. And so you get a simple result. And then finally, you need to integrate over the two spheres. The 1 over r squared here cancels the r squared here, and you just integrate over a sphere. And you'll discover that this thing involves a lot of unit vectors n, this expression. 0, 2, 4, lots of unit vectors floating around, multiplying each other. And here's where you use these handy-dandy formulas that I showed early on. When you want to integrate products of a unit vector, this is the same as that, over a two-sphere, you get 0 if the number is odd, something if the number is even, and that something always involves Kronecker deltas. Single Kronecker delta here, and then products here, and then higher order ones there. Okay, so just use these rules to do the integral over the two-sphere. And when you do all that, here's the example for dE dt. So I've already said this, you have Landau-Lifshitz. When you do this calculation and follow all these rules, you discover very nicely, actually, that before you do the angular integration, the result is simply the first time derivative of h plus squared plus the time derivative of h cross squared. These are the two TT transverse traceless components of the gravitational wave. Okay, and you can also express this in terms of Hij itself with all the various unit vectors that come from those projection operators. Then when you integrate all those unit vectors over omega, the answer, final answer, looks like that. G over 5 c to the 5th, a minus sign because the energy decreases. And this is 3 time derivatives of that quadrupole moment tensor, contracted, but it's the symmetric trace-free quadrupole moment tensor. Just to remind you, IPQ is just IPQ, the regular guy, minus 1/3 delta PQ times MM, the trace of the moment of inertia. Yeah. I'm sorry?
Can you derive this expression from the quadrupole?
Well, no, this is the quadrupole formula. This is what we have derived the quadrupole formula. Okay? From the first principles.
This is the power expression. Earlier on you had the H expression, the expression for H.
Yeah.
In terms of the second derivatives of the...
Right. No, so, yeah, the quadrupole formula refers to two different things. There are two quadrupole formulas. One is the formula for H in terms of 2 time derivatives. And of course, that's what you would plug in here. H involves 2 time derivatives of the quadrupole moment, and this d by dt is what gives you 3. But I mean, we've plugged in our solution for H to get it. But this is also called the quadrupole formula, but this is for the flux. One is for the amplitude, the other is for the flux. We use the same word. Of course, there are higher order corrections to this formula, post-Newtonian corrections. I'll show you one example in a minute. So it's quadratic formula for flux. It's also known as the Newtonian order contribution. That way we can call these corrections post-Newtonian and second post-Newtonian corrections. You can also calculate the flux of angular momentum. Turns out this is a bit trickier to do, but you can do it. We go through details in our book. There are a few subtleties, but it's straightforward to do, and you get a formula that looks something like this, a bit more complicated. And you can also calculate the flux of linear momentum. Gravitational radiation can emit linear momentum. That's because the waves carry energy, but energy is the same as momentum in a relativistic world, right? And for a null ray, the momentum is just equal to the energy times the unit vector of propagation. Okay, so momentum can also be radiated from a system. And consequently, the system can experience a recoil due to that radiation. We'll talk about that actually in the second lecture this morning. Now, we know the quadrupole moment for a two-body system. It's just, for two bodies in relative coordinates, this thing is just mu times xp xq, STF. So take 3 time derivatives of that thing. Wherever you see an acceleration, right, after 2 time derivatives, you'll get an acceleration in one of these terms. Plug in the Newton's equations of motion. We know there are corrections to those equations, but they're just going to appear at the higher order along with other junk. So we're just looking at the lowest order contribution. So plug in the equations of motion and just take another derivative, plug in, blah, 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 and then get into that formula. And contract over P and Q, and that's what you get. The loss of energy by a two-body system is proportional to the square of this reduced mass, dimensionless reduced mass factor, gm over c squared r to the 4th, and 12 v squared minus 11 r dot squared. R dot is the rate of change of separation. Notice I've been talking about things that order 2.5 post-Newtonian order, as where radiation reaction enters. Order c to the 5th, 1 over c to the 5th. Well, you notice this is 1 over c to the 5th. C to the minus 8, c cubed. So this really is a 1 over c to the 5th effect on the behavior of the system. Here's what it looks like for an eccentric orbit. So this is the loss of energy. Of course, the flux, if you measure the flux received at infinity, it would just be the positive of that, right? So here's a plot of the flux for an eccentric orbit. If you plug in our orbital elements from that earlier formula, you get this. And as a function of phi, the orbital phase, then it looks like this. You get a big peak of flux near pericenter, right? When the two bodies are close together, gravity is stronger, they're moving faster, so clearly you get a big spike of flux near the pericenter, and then at apocenter, it's much less, and then a big spike at pericenter. For a circular orbit, of course, the flux would be just some steady amount. So it depends on the nature of the orbit, the nature of the energy flux as a function of time. If you take that flux and average it over an orbit, so suppose you don't care about the specific details, but you just want the average flux over one orbit. Then when you do that averaging, which you can do here, you can just integrate over phi from 0 to 2 pi, then you get this formula. So this is the orbit average flux for a two-body system, same factors as before. Here I've written in terms of the semi-major axis A, and then there's a function of the eccentricity of the orbit that's given by that. Okay, so that just comes out of the averaging process. But now we know for a two-body system, the energy is equal to minus 1/2 mu times the total mass over the semi-major axis. So E varies as 1 over A, right? We also know that the period of an orbit is equal to 2 pi times A to the 3/2 over m to the 1/2 with a factor of big G. So P varies as A to the 3/2. So you can see then that the energy varies as 1 over A, which then varies as P to the minus 2/3. We want to do this because we'd like to convert this expression into something we could actually measure for a binary system. You don't measure the energy of a binary system, right? Well, what you can measure is its orbital period, because you look at the binary system, you just see how long it takes for it to make one orbit. So we can convert dE dt into dP dt, because dE over E is equal to minus 2/3 dP over P. So we can get a formula for dP dt, and that's something you can really measure. Furthermore, this thing depends on A, but using Kepler's third law, we can convert A into P, so that the stuff on the right-hand side also depends on P, which is something we measure. So when you do those manipulations, you discover that dP dt for a binary system is minus, the period always decreases, and then you have this factor involving P itself to the 5/3 power, and this thing, which we've seen before, it's called the chirp mass. And this is the fundamental mass that governs how the period of an orbit changes or how its frequency changes. And it's given by eta to the 3/5 times the total mass. And so for an in-spiral, they call it a chirp mass because this is the mass that really controls how the frequency changes, really controls what the chirp sounds like. Hence the name chirp. Of course, the term chirp comes from engineering. I think they use chirp to describe signals that rise in frequency like this. I think that they call it that because there must be some bird somewhere in the world that sounds like whoosh, right? So that's where the chirp name comes from. But of course, as many of you all may, I'm sure, know, this formula played a key role in one of the great confirmations of general relativity through the binary pulsar. So in 1974, Joe Taylor and Russell Hulse discovered a pulsar in a binary system around a companion star. Companion star is most likely a neutron star itself, but it's not a pulsar. There's no detectable signal from the companion neutron star. But over time, they were able to measure the rate of decrease of the orbital period of that binary system. They could measure the eccentricity. Of course, what you're measuring is the orbit by looking at the Doppler shifts of the observed period of the pulsar, because it's coming toward you and away from you. And so by looking at the rate, how the pulsar period changes, you can then determine the velocity and motion of the pulsar in orbit about the companion. The shape of that orbit gives you the eccentricity. And you can measure the period and the rate of change of period and check that formula. Unfortunately, you don't know the masses, just as before. But because you can measure the pericenter advance, which you recall depends on the total mass of the system, you can measure the total mass. And there's an additional effect in this system that's the gravitational redshift of the pulsar signal, because it's going in and out of the gravitational field of its companion, because the eccentricity that was measured was about 0.6, very eccentric orbit. So this pulsar is going around the companion, but also getting close and far. And that induces a gravitational redshift effect on the observed pulsar frequency. When you measure that, you can measure a different function of the masses and thereby determine both masses separately. So in fact, both M1 and M2 are known today to about a part in 10 to the 4. And so you know from that what this mass is, the chirp mass is. So you measure P as a function of P, and then make a plot. And this is one of the most famous plots in astrophysics, in my opinion. What this is the time of periastron. So this is the time when the binary system passed through periastron. If the period were the same, then this time would always be the same. I mean, sorry. If the period were the same, of course, then this would grow linearly. How do I want to say this? Well, the point is that yeah, if the period changes with time, then when you get to the next periastron, you arrive maybe a little later because the period is less. But then the next time you arrive even later, but the period is also decreased a little bit. So that it's a little less, but then it's a little less by even more. And you can show that the time of arrival at pericenter, if there's a non-zero rate of change of orbital period, should decrease as a quadratic function of time. Okay. And here are the data points. Of course, in 1974, when it was discovered, you just set that equal to 0. And in the first 4 or 5 years, they measured the little tiny change in the orbital period. This was done by about 1979, 5 years after the discovery. And so they were able to measure the rate of p dot, and it was in agreement with this prediction of general relativity, knowing the masses from those other two relativistic phenomena and knowing the eccentricities. So this is a great confirmation of the quadrupole formula, and in some ways the first detection of the effects of gravitational radiation, because there's no other explanation for this decrease of period. And this discovery and this measurement of dp dt won Hulse Taylor the Nobel Prize in 1993. But since that time, they've continued to measure this time of pericenter, and these are the data points. And the errors, the measurement errors, are much smaller than the width of those dots. In fact, there are a few error bars in some of these places, but the errors have been multiplied by, I think, 400, just to make them even visible on this chart. So the measurements of how this time evolves with time are very, very precise. And this curve, it's not a fit to those dots. It's the actual prediction of general relativity simply using this formula with the measured E, the measured P, and the measured chirp mass. And it agrees completely with the observations up to, in fact, I have a more recent one of this that goes, I think, up to 2010, and it's still lying along the GR line. This gap here, of course, is a period in the late 1990s when the Arecibo radio telescope was shut down for an upgrade. And, but even so, when they returned to the telescope and measured the pulsar, the phase of the orbit was exactly what they had predicted, and it lined up perfectly with the GR prediction. Now, for this system, of course, you only need the quadrupole formula. There's no way for the foreseeable future that these kinds of measurements will become accurate enough to worry about the post-Newtonian corrections to these kinds of formulas. But for laser interferometers, we do need to worry about these corrections. The kind of precision you get, and the precision you get from the measurements, and what you need to fit these theoretical models to the data, you absolutely have to have those corrections. And here, let me just show you one example of a formula that shows what these corrections look like. This is a formula taken from Luc Blanchet's living reviews in relativity on this subject. So this is a formula for dE dt, the energy flux. This new parameter is my eta. Okay, I've tried for years to get Luc to agree to using eta instead of nu, but I mean, he's French. They have their reasons for doing what they do, and you know, they like nu. It's much more elegant than eta. Okay, so nu is this reduced mass parameter. X is a measure of V over C, essentially, but it's really defined in terms of the gravitational wave frequency, omega. Okay, so this quantity, this is a measurable quantity. This is the frequency of the gravitational waves that you actually measure. So this quantity it gives you this beta, but it gives you X, but it's really a proxy for V over C squared. So this first term is the quadrupole formula. It's exactly this. When eccentricity is 0, in this case, it's all for a circular orbit, because as we'll see in the next lecture, for the kinds of things that LIGO is likely to detect, you expect the orbits to be highly circular. Gravitational waves tend to circularize orbits. So there's the quadrupole formula, the 1. There's the first post-Newtonian correction to the energy flux, x is v over c squared. This was first calculated by Bob Wagner and me back in 1976 when I was at Stanford. And at that time, we did this calculation only because we could. It wasn't too hard to do to get that next order calculation. In 1976, we said, we can do this calculation, but no one will ever care. This will never, ever be used. The binary pulsar had just been discovered, but it was clear you'd never need these corrections for the binary pulsar. It was a purely academic exercise that we did just for fun, because we could do it. And we said, you know, no one will ever. Now, of course, our paper is so highly cited because it was just the beginning. Once the LIGO started up and running, people thinking about detecting inspiraling binaries told us that this would not be good enough if you wanted theoretical templates that would match the signals properly. Even the detection required more accurate templates. But also, if you really want to use these templates to measure things like masses and spins, such as the ones I showed you, you needed higher order corrections. And indeed, not just the 2pn corrections, but even higher. There's a correction at order 1.5 pn, right, v over c cubed. That's the tail term that we talked about. That produces a little term here with a 4 pi. Luc Blanchet and Sathyaprakash, whom you'll hear from next week, did an analysis that showed, this is the early days of LIGO, they measured how accurately you could measure this tail term given a LIGO noise curve and a given source. So what they showed, and it was very exciting, that you could measure pi to about 20%. We know pi more accurately than that, right? But still, this is a fundamentally nonlinear term, right? This is the effect of gravity on the propagation of the gravitational waves themselves as they go to the source. This term does not occur in electrodynamics in flat space-time because E and M doesn't interact. Electric fields don't interact with themselves. This is a purely nonlinear GR effect. So the fact you can measure it, and it was measured in GW 150914, so it's very exciting to measure that tail. There's the 2pn correction. There's a correction at v over c to the 5th. This is a post-Newtonian correction to the tail term, and it's a tail correction to the post-Newtonian term. Here's the 3pn term. And these numbers are not made up. I mean, these are real numbers that you calculate, and independent methods give the same number. I think this is a tail of a tail term. There's one of these Euler numbers, a logarithmic number, and so on. And then and 7/2 post-Newtonian here. And currently, various teams are working on the 4pn corrections. Again, because it's not because we want to do this. I mean, these are unbelievably complicated calculations, but we're forced to. People at LIGO say we need these higher order corrections if we really want unbiased estimates of masses and spins, and so on. So it's really something that's been forced on us by gravitational wave interferometry. But it turns out, you may have been thinking all along, but at some point this post-Newtonian approximation has to fail. It's an expansion in V over C, but what if V is, comparable to C? I mean, surely this thing is going to break down somewhere. And obviously it does break down somewhere, but it turns out that this approximation, coupled with the fact that we can get so many of these higher order terms, it turns out that it's unreasonably effective. So it's a term I use, it's a talk I give often, the unreasonable effectiveness of post-Newtonian theory. And here's just one example, and I could cite many. Here's a comparison of the post-Newtonian waveform from an inspiraling binary. This is two equal masses. The dashed line is the post-Newtonian waveform, going like this, and at some point you just quit because surely it's breaking down. The blue curve is a curve of the same equal mass binary, same masses, from numerical relativity. And this is the early days. Of course, these calculations have gotten much better in 10 years, but this is early days of these kinds of numerical relativity solutions. And you can see that it tracks the post-Newtonian very well. They get a little bit out of phase at the late stage. But here is where the separation of the two black holes is just 5m. In other words, V over C squared is of order 1/5. So V over C is of order 1 over the square root of 5, which is about 1/3 or so. V over C is not small. Yet because we have these higher order terms, we get a prediction that is very close to what you could argue is the exact solution, the numerical solution. And this is way beyond what we ever expected. In fact, in the 1990s, Kip Thorne and some of his students were really worried that post-Newtonian theory would fail here. And in those days, numerical relativity could only do the last 2 or 3 orbits. This is in the late 90s. And there was this gap between the two theories that we didn't know what to do. We didn't know how well post-Newtonian theory would behave, and there was no sign then that numerical relativity could do any better. And they were very worried about how you would link these two things. Well, today we know the answer. Numerical relativity had some breakthroughs in 2005, so they can really start much earlier. And post-Newtonian theory turns out to be much more effective, much more accurate than we ever thought. And so now, using the combination of the two theories, one can now build analytic models for the entire waveform from the early in spiral through the merger and the ring down part that then are built into the LIGO data stream. Okay? Any questions? I haven't stopped for too many questions because, like a bad student, I was late for class, so I'm trying to make up the time. But any questions? Okay, so let's take a break. So maybe we should pick up at 11:30. We'll have a short break. So I have to get back into the city to get ready for the lecture this afternoon. So I have to leave at 1:30. So let's take a 15-minute break and we'll start at 11:30 on time.